So, all my volunteers in a second. Today, 7.5, our goal is analyzing and sketching graphs. So we've done a lot. First, what's a function? How do we identify a function? What is a linear function? How do we graph those? What's a linear function versus nonlinear? And now today, we are going to work on creating a graph, on how some of them are different. So I need 3 volunteers. All right, Dusty, go to the back wall. Evan, go to the back wall. Kemper, back wall, please. Thank you. I will hit you guys up with a dum-dum in a second. All right, so Dusty, you're going to be blue, and I want you to do something for me. You're going to walk, it says, walk slowly from, it says front, but I have you in the back, from the front wall. I want you to walk from back there to the front, just at a nice, slow pace. Ready, begin. So if we're watching Dusty walk at this pace, perfect. Now up here it says we have to graph what he just did. So I'm going to go in blue, and it says distance from the back wall and the time he took it. Is there a relationship between time and the distance? Should there be a correlation? Yeah, it should be what? Would this be a positive correlation or a negative correlation or no correlation? Positive. And that would make sense. Like, if he's walking slowly as time goes, so when time gets bigger, the distance from the back wall should also be getting bigger. So when I go ahead and graph this, I can go ahead and say he started here, and since he's walking slow, will he be covering a lot of distance fast? No. So I'd probably just go ahead and say from here, maybe he's like this. All right, so volunteer 2, Evan. I need you to walk quickly from that wall to the front. Go ahead. Okay. How do you think that compares to Dusty? Much faster. When I graph his in green, he still started at the same place as Dusty. How is his graph going to be different? His line. It's going to be more steep. It's going a farther distance. Let's say our final distance was, we'll just say this is the wall. Even though if he would have busted the wall like a Hulk or a Kool-Aid Man or something. But we'll go from here. So if I was going there, he hit that back wall faster, right? He went in the time, if we went to the same time, he would have covered a farther distance. Actually, this is kind of drawn backwards, I'm sorry. But, he would have covered, since this is time, he would have covered in time, at the same time, if I gave him 5 seconds, Evan would have went farther than Dusty did. If we're looking at the wall, we'd have to look over here and say boom, boom, boom. It took him less time than it took Dusty. Okay? Now, I'm going to have Kemper. He's our last one. I'll put him as, it's supposed to be red. Okay, I need you to stand at the back wall and not move. Go. Oh, man, that's mad skill you got, Kemper. Look at that. Pure determination. All right, and then we stop. Kemper will be here. Is he going to have a line?
No. It's just going to go straight on X.
No. Why would you have a line? Well, did his distance increase? Did time increase?
Yes.
Also, would he have a line?
Yes.
On X.
He would stay on that X. So his line would just be like this. All right, you guys can sit down. I'll throw you your dum-dums in a second. All right, so when we look at this, this is how we are graphing. Okay? I'm going to do a new one. Just to throw a twist in. Now, let's see if you guys can figure this out. This one will be for sucker. Let's say I use the exact same graph. And I'm going to say this is still the distance from the wall. And then this is time. Who can tell me, or reenact? You have to reenact this one. I need you to reenact what's going to happen here. So, we'll use it as comparison to these guys. Actually, maybe I'll just do it right over there so you can see comparison. So, comparison. Hey, what happened here? Okay. Does anyone think they could do what this orange line is showing?
Yes. Yes. Yes.
I don't know, you gotta think.
I
Make sure. Let's see, who are my three? Kemper, and Dusty. Will, do you think you can go back there and show us what happened? Almost everything is perfect. Almost everything is perfect, but I'm comparing to these other guys. He said I went 4, I stopped. It stayed straight. I didn't go any distance, but I sat there for a while. Then I went backwards because the distance between him and the back wall decreased. So he went backwards, and then I went forward again. What's the only thing that he probably needed to do different if I'm being really picky? What do you mean?
He should have went faster going.
There you go. If I look at this, if I compared all three people, Dusty walked slowly, Evan walked quickly, this one's even faster. So this one showed right here, he probably went fast. Probably started that back wall, sprinted forward, stopped. It was like, whew, I sprinted that whole 4 feet. Gotta take a breather. Stopped, breathe. Then he ran backwards, and then took off forward again at a very fast speed to finish the rest of the distance of the wall. So that is showing up. So let's have one more person do this one. Let's draw this one. One person do the walking, and one person has to do the drawing. And I want you to draw in real life time, see what they could be doing. Aiden, I'll let you walk. So get to the wall. Drawing what they think will happen. Hold on. We gotta watch it. We're gonna see. If I tell you to stop, you have to stop them. Okay. Kipper, do you want to draw?
Yeah.
All right. Use this wall. Okay. Ready. Hold on,
Which pen do I use?
Either one. Alright, you have to start at 0. Ready, Aiden? I might say stop, which means I want you to pause. Go. Stop. Go.
Richard! Oh well, I'm still doing it.
Stop.
Are you even drawing?
Go.
Nope.
Alright, and that's the end. What do you think that would... Kimber, how do you think that could go?
What do you mean?
How could you draw this?
Well, like, whenever he'd go, like, the pace, I'd like do that. And
So you go
stop.
up at a steady pace, so let's draw that. We start at 0.
He's actually going to draw this time.
Did you
So,
And then he stopped. And then he went. And then he stopped. And then he went. Good. Thank you. Hey, you got one, didn't you?
Remember that AirPod?
Let's look at
Remember
this.
that other?
Alright, so. Oh, my paper. Alright.
It's a sequel.
Says, work with a partner. So I'm going to give you guys a couple seconds. It says, each graph shows your speed during a bike ride. So you're riding a bike. Match each situation with its graph. Explain your reasoning. So we have A, B, C, and D, and I want you to match it up with each scenario. All you have to do is write like A, B, C, D, wherever they belong. Then we're going to discuss them. Okay? The only thing I'm pointing out is our x-axis is time, and our y-axis is our speed. Okay, I'll pause our video, give you about a minute or so. Let's read through the things and then I'll have you work. So one says, you increase your speed, then ride a constant speed, then you slow down until you reach your friend's house. You ride a constant speed, you go up a hill. On top of the hill, you increase your speed. You increase your speed, then you go down a hill. You quickly come to a stop at an intersection. You increase your speed, then stop at a store for a couple minutes, then continue to ride, increasing your speed. Alright, turn, work on the neighbor. See if you can match these four up. Alright, so let's come together. There's two ways we could do this. One, I could look at my graph. I could look at my graph first and describe what's happening in the graph, and then match it, or I could go this way and look for it. What would you say the first one was? And we'll check your work. What did you say? The very first one. You increase your speed, then ride a constant speed, then you slow down until you reach your friend's house. Who said, what letter was this one, Sydney? Alright, so let's check this. See if she got C right. I increased my speed. Increasing my speed. Remember, on my graph, speed is on the left, time's on the bottom. So, my axis. So, increase my speed, it should be going up. Constant speed means it should just be a straight horizontal line. My speed's not changing. And then I slow down, so it should go down. If I put all those together, I increase my speed, constant rate, decrease my speed. C is correct. Oh, I gotta get some out. So I'll get I don't know what you said. Next one. Focusing so we can get through this. You ride at a constant speed. Then you go up a hill. Once on top of the hill, you increase your speed. Aiden. So if I said B, a constant speed means I'd be doing a horizontal line. If I go up a hill, what do you think is going to happen to my speed? It's probably going to make me go down. Once I get on top of the hill, Brett, I'll be coming down, I'll be going faster. So we're going to look for straight, down, then up. Straight, slower, faster. Good. Aiden, I'll get yours. Over there, Zachary. Third one, you increase your speed. Then you go down a hill. You then quickly come to a stop at an intersection. It doesn't shut. Donovan.
A.
So you think A, let's check and see. If I increase my speed, what would happen if I go down a hill? How's that going to be different?
It's going to decrease.
It doesn't shut.
Oh.
Good enough. We'll just leave. Oh. Alright.
Busted.
So, if I increase my speed, what happens when I go down a hill? What's going to happen as we go down a hill? What's my speed going to be doing? Increase. I like that he said that. Increase more. So the steepness is going to be even more. Then I quickly come to a stop. So I'm going to be there. Quickly come to a stop means when I decrease, whoa. When I decrease, it's going to happen fast. So, increase slowly, fast increase, fast decrease. Which means the last one, gentlemen, not side conversations. Which means our last one is we increased our speed, stopped at a store for a couple minutes, so I stopped, I'm not doing anything. Continue to ride at increase. Oh, this would make sense. I was like, something's off here. If I stopped at a store, what would happen to my speed?
Completely stop. You go like.
So this was, I was increasing. If I stopped at a store, my speed would drop fast because I'm stopping. So I come to a pretty quick stop, and I stopped for a couple minutes. This was where I stopped. And then I increased my speed. Okay, let's discuss this so we can get through here. What do you think could be happening in this graph? Everyone think, I want you to talk with your neighbor. It says height and time. So as time goes, how is the height going up and down and up and down and up and down? Quietly talk with your neighbor. What do you think could be happening? Okay, what was their ideas? What could be happening here? Evan?
It could be like going really fast and then slowing down. But still slowing at the same time.
Okay, so it looks like we're going fast and then slow, but remember, this isn't really about speed. This is height versus time. So I'm on a ramp going up and down. Yeah, let's make sure we're focusing on this.
Focusing.
All little should be open, so you're counting on this. Donovan? Yeah. I think this could be. This could be one that someone's jumping, or I'm even thinking this could be a jumping. They could be on a pogo stick. Trampoline. They could be swinging, where my height, when I swing, I get to the high part, and then I come back down, I get to the low. But then that would go. Oh, but that could be. I get to the high part, and then I come back to the middle, but then I go backwards to the high part. Maybe that same height. Will? Maybe this is a person working out. So they're standing there with the bar, and they're doing squats. They go down, and then they push it up. And then they go down, and then they push it up. The thing that's important to notice is that my height, the top part, every single time, starts to the exact same height. Where it stops is also the same place. And the other thing is the time, the interval it's taking in between is same. So this is a repetitive thing, going the same. So when we think about this, whatever is happening, it's going up and down, but it's doing it at a same pace into the same height.
They could possibly be swimming.
Could be. And it could be, but remember, the biggest thing is that it's at a constant rate. Okay, key concept. We need to make sure we're understanding this. On our key concept, that graphs show a relationship between quantities without using specific numbers on the axis. So this, what we're looking at, we don't have a scale, but we're showing what's happening. This, distance versus time. So when it's going up, that is showing Dusty. If I have to stop again, I'm going to mark you and move you. This is showing that my distance is increasing. When it goes straight across, that I have no change, it's constant. My distance is the same, and my time is moving on. I can't stop time. Unless I'm doing something with a stopwatch and we're actually timing something. And then when it went down, this is showing me decreasing. I gotta make sure how much we have to get through. Okay. So, if we look at example 3, the graph shows the temperature throughout the day in 2 cities. Now in Maine, I see the temperature and the time, and it's more of a curve. Okay? So how would we describe what's going on in the temperature in that city?
It goes up. It's getting warmer.
So in Maine, it's a more gradual change. With our curve, it's constantly kind of getting warmer and then getting cooler. This would be what we would kind of expect in a typical day. In the day, in the morning, it's always cooler. It warms up at around noon to 1. It's the hottest point of the day, but it gradually gets a little cooler to the evening. So we're going to say like a gradual change. It's getting warmer to cooler. How about in Oregon, though? How fast did it get cooler? So this one in Oregon had a fast change in temperature. That temperature dropped dramatically, and it did it quick. It fell to a point, and then it stayed at that point for a number of times. Zachary, why are you messing with my pencil sharpener? Please put it up and then sit like you're supposed to be. I'm here to play with things. And then it would gradually, it started increasing. This, I might think of like a storm that came through. Snowstorm came through, so all of a sudden, you guys have been here, being in the Midwest, where all of a sudden our temperature dropped. Like in the hour, it dropped like 10 degrees. That's pretty fast. And then it stayed cold, and then once that storm kind of passed, it started warming up pretty quick. I think this one, yes, this one's in yours. So in your foldable, we're going to do this. It says, sketch a graph. A stopped subway train gains speed at a constant rate until it reaches maximum speed. It travels at the speed for a while, and then it slows down at a constant rate till it comes to a stop at the next station. The whole time our turn is continuing on. So, try and draw this. Right now, in your foldable, go ahead and draw. What do you think this graph should look like? I'm going to pause my video real quick. Okay, what I did real quick is I went ahead and highlighted and drew some things on the instructions. A stop. Okay, so that's important. It was stop, so I know it's going to start right here. It gains speed at a constant rate. So I'm going to have a straight line. And it's going to go gain that speed until it reaches its maximum speed. So I'm going to say its maximum speed's like here. So I'm going to draw my line like this. Once it reached that maximum level, it traveled at that speed for a while. So I would make a straight line. It went up just a little, but we'll pretend it's completely straight. Then it slows down at a constant rate until it stops. And if you, I was trying to use the line feature. Only thing is, I need this to.
Mr. System, what would happen if that did happen? There's like a gap.
Just tell them.
You would have messed something up.
Would it be like
Time vortex.
for a second?
All time cease to exist. Until we'd have to say until an ending point, and I would have that stopping point. After that stopping point, it would be constant again. The speed would stay constant. Last one you're going to do. Sketch the graph. A fully charged battery loses its charge at a constant rate. Because it's fully charged, where's my starting point? At the very top. Good. So at the very beginning, I'm going to start here. It loses charge until it has no charge left. So I'm going to go from here and I'm just going to go there. So I'm going to say, boom. Okay? It lost its charge at a constant rate, which means I should have a linear function. If it's a slope, same the same. You plug it in, and it fully recharges at a constant rate. So, over time, it's going to be charging back to there. Then it loses charge at a constant rate. How come on this one, I didn't have a straight horizontal line, a constant horizontal line? Kemper?
Never at one point did it say like not dying.
Yeah, very good. If it would have said it died and I waited an hour and then plugged it in, if we would have done that, if I would have added no charge left, wait 1 hour, we would have done the same line. It died, but then I would have waited an hour, then went up, then had it die. Awesome. I don't think you guys are going to have much trouble with this, so here's your assignment. For tomorrow.
I do that and then use the alternator. I do that. It's not that hard.
There is, gentlemen, listen to instructions first, then you can talk. 7.5, matching description of the graph. The graph shows your speed during a run. Match the verbal description with the graph it describes. So, Brett. So, what is happening here? You're going to look at this graph. There's 4 points on the graph, A, B, C, and D. You run at a constant speed. Which one of these points would that be? You slow down at a constant speed. Which one of A, B, C, or D would that represent? You increase your speed at a constant rate. What would that represent? And then you run your speed faster and faster. What would that be? Down here, describe the relationship between the two quantities. You're going to have to use some words on these three. But what is the relationship between the two quantities? Between the volume and the time, the dollars and the time, horsepower and engine speed. And then the last part, the value of a television decreases at a constant rate and remains the same. Right here on this first graph is where I want you to draw. On 19, the distance from the ground changes as your friend swings on a swing. How would you draw that? Okay? Any questions? Okay, this is what your assignment is for tomorrow.